Okay, the notes here look a little bit different than yours. I added a few problems to it, but I don't have the original of your notes, so I couldn't add to it without redoing the whole thing. So you might want some extra paper here. All right, so what do we have here? What is our outermost function? Or let's do this one from the inside first. So the inner function, you look at what happens to x, right? So the first thing that happens to x is I take 3 minus 2x. And then the next thing I do after the 3 minus 2x is I take the square root. And the next thing after that is the sine function, right? So the innermost to the outermost. So this is a composite of 3 functions. So far we've only done a composite of 2 functions when we've differentiated it. So what we're going to do here is, like the chain rule says, you're going to differentiate that outermost function first. Okay, so momentarily, I'm going to treat this as if there's an x here. So the derivative, if that had been an x, would be the cosine of x. But it wasn't just an x, it was a whole expression. So we just leave that expression there. And then we have to differentiate that inner function. Okay? So I get f prime of x, cosine of radical 3 minus 2x. Now we differentiate this, but this is still a composite function. So to differentiate that is going to require the chain rule itself. This is, if it helps you to think of it this way, it's 3 minus 2x to the 1/2, right? So the derivative of that, the outer function, is the 1/2 power function. So we're going to get 1/2. What's in there to the negative 1/2? We leave what's in there. But it wasn't just an x. So what do we have to do now? We have to multiply by the derivative of what's inside. And so we're going to get, this is negative 2, and that's going to divide out with this 2. So I'm going to get a negative still, this negative is still there, negative cosine of radical 3 minus 2x. And then I've got that 3 minus 2x to the negative 1/2, so that's 3 minus 2x down below. So when you have 3 functions, what did I do here? To go from here to here, I needed the chain rule. But then when I got to this point here, to differentiate that, I needed the chain rule again. I have these 3 different functions, and somewhere in the problem you have to find yourself taking the derivative of sine, I did. The derivative of the 1/2 power, I did that here. And the derivative of 3 minus 2x, we did that here. You have to eventually differentiate all 3 of those. If there are 3 layers, 3 functions, then we're going to apply the chain rule twice. I think the best thing to do while you're learning how to do this is to not do anything in your head. So like for instance here, I put cosine of what's inside and then the derivative of what's inside. I didn't try to differentiate that piece in my head. I just wrote it down, and now I'll work on it at the next step. When you get really confident with this, you can do this all in one step. But while we're learning, I think you're going to find it's better to do one application of the chain rule at a time. Okay. You want to give it a shot? Why don't you pause and try the next one? Okay, so you don't have to do this listing. While we're learning, I did that. So if you feel the need to do that here, go ahead. The innermost function would be x cubed. Then, be careful, then it's cosine, then it's the square function. I find that it helps a lot of students to write it as that square outside so we can really see that that's the outermost function. Okay, so to differentiate that, we differentiate the square function first. So again, I'm pretending like this is an x for a moment. The derivative of that would be 2x. But it wasn't just an x. It was a whole function of x. So I now need to differentiate that function. Okay, so we've dealt with the outermost layer. We have differentiated the squaring function so far. We've got 3 layers. We've taken one derivative. We've applied the chain rule here once. We have differentiated the squaring function. All right, so now we get 2 times the cosine of x cubed. And now we've got to do this derivative. But that derivative is a function within a function, so that's going to take the chain rule. We differentiate that outer function, which is cosine, so we get a negative sign. Leave what's in there, and then differentiate what's inside. Okay, so I apply the chain rule again. Then I get to the next step here, 2 cosine of x cubed times minus sine of x cubed. And at this step, we differentiate this. Now, do I need the chain rule to differentiate x cubed? No, I finally got to the point where it's not a composite function anymore, so I just differentiate that function. And so we would get negative 6x squared cosine of x cubed sine of x cubed. A good thing to double check is what were my 3 functions: cosine, the squaring function, and the cube function, not in that order. So what did I do here? I differentiated the squaring function, so we did that one. And then in this step, I differentiated the cosine function. And then the third step, I differentiated the x cubed. So each of those 3 original functions did get differentiated somewhere along the line. 3 layers, 2 chain rules. Okay? Why don't you pause and give the next one a try. Okay, this one has 4 functions. The outermost is the square root, and then would come the tangent, and then the cosine, and then the 7x to the 5th. Okay, this is the innermost working out, this is the outer working in. So the derivative here. Okay, so first thing I need to do is differentiate the outermost function, the square root function. The derivative of the square root of x is 1/2 times x to the negative 1/2. But remember, it's not an x in there, it's this whole expression. So tangent of the cosine of 7x to the 5th. Then I need to differentiate by what's inside. So the derivative of tangent of cosine of 7x to the 5th. Okay, we okay with that step? I've treated this momentarily like it's an x. The derivative of the square root of x is 1/2 x to the negative 1/2. But because what was inside there was not an x, but this whole expression, that has to be written here. And then I have to open that up and differentiate it. Okay, so what have I done so far? I have differentiated the square root function. I have applied the chain rule once. Keep going. So this part here, I'm going to go ahead and clean that up a little bit. I don't have to do anything more to it other than maybe simplifying, but I'll write it this way. The tangent of the cosine of 7x to the fifth. Okay, so I didn't do anything to that. I'm just rewriting it. And I need the 2. Now I've got this derivative to take. So that is 3 different functions going on there. The outermost one is tangent. So to differentiate tangent, I get secant squared. Right? If this was tangent of x, this would be secant squared of x. But it's got more than just x in it. It has cosine of 7x to the fifth in it. So I need to differentiate that inner function. Okay, so what have I done now? I have differentiated the tangent function. That's how I got that secant squared. And I had applied the chain rule there. Okay, so I've got secant squared of the cosine. It's a lot of writing, isn't it? 7x to the fifth. Got that. Over the square root of the tangent of the cosine of 7x to the fifth. Okay, and now I'm left with needing to differentiate this part. So that's still a composite function, right? There's the 7x to the fifth is in the cosine, still composite. So I'm going to differentiate the outer function, which is cosine, so I'm going to get a minus sign, leave what's in there, and then multiply by the derivative of what's inside. That's why I wanted you to get good at those ones that just had 2 layers before you started on the ones with multiple layers. Okay, so what did I do in that step? What function did I differentiate? I actually differentiated the cosine function that time, right? That's the one that's the formula I used, the one for cosine. And that was another application of the chain rule. And so I get the derivative here. Now that's not a composite function anymore. I don't need to apply the chain rule, I just differentiate. The reason I say that is because sometimes when we have all these layers, it's like people feel like they need to keep going. Like, okay, 35x to the fourth, and now 35 times 4x cubed, and like you feel like you have to just keep going and going. It's not. At this point, it is not a composite function. It's just a straight derivative. So we differentiated at that stage. We differentiated the 7x to the fifth. So to double check, we did differentiate each one, and there were 4 layers, and we did it by applying the chain rule 1 here, 1, 2, 3 times. Okay. I would write this as this out in front with the negative and maybe the 7 on top, the sign on top, just so you can kind of see it all. You don't want this minus or this to get lost anywhere. Okay, so that's 4 layers. Might there be one on a test that's that many layers? Sure, because it's really testing us if we understand the chain rule. Now, when you get really good at it, you might be able to go straight from the original function to here, believe it or not. You differentiate the outer function, and then you're looking at, oh, I'm going to have to differentiate that, which happens to be a secant squared of this, and then the derivative of that is, and so on. But I find a lot of times that people miss these when they try to do too many steps at once. It's very common to miss one of the layers. For instance, maybe you remembered to differentiate tangent and get secant squared, but then you never ended up doing a derivative of cosine anywhere. That's why I say it's kind of nice to list all the functions and make sure at some point in there that you did find the derivative of that type of function. Oftentimes, by the way, the biggest mistake is not recognizing that you need to use the chain rule. So for instance, let's just go back to something simple. If I asked you to take the derivative of the cosine of x squared, I often see negative sine of x squared. And that's a big loss of points there. It's not recognizing that you need the chain rule. You would actually need to multiply that by a 2x, right? So you've got to notice when what you have is a composite function. Okay, we need to practice those. One more thing that I want to show you here. This is kind of neat. You might like this. Now that we have the chain rule, we technically could get rid of the quotient rule. Now, I don't like to get rid of the quotient rule. Sometimes I prefer using the quotient rule, but here's what I mean. Anytime you ever have something in the denominator, you could write it as multiplying by 4x minus 3 to the negative 2, right? Here's what I encourage you to do. I don't want to take the time to do it both ways. Do it with the quotient rule, see how you like it. See what kind of algebra you have to use when you do it that way and so on. Maybe you like it better that way. But I'm going to show you this new way of doing it because it involves some algebra that I want to mention. So that's my f. So f prime is the derivative of the first times the second plus the first times the derivative of the second. Now this is what I'm talking about, how you're going to find that you can skip steps as you go. As I was writing derivative of this, we were probably already thinking, oh, well, that's 3. You can just write the 3 at that first step if you like. All right, and then this guy here, that's a function within a function. So that's going to require the chain rule. So let me just make sure it's clear. The first step was the product rule. But in the middle of doing a product rule, a chain rule, the need for the chain rule came up. So this is going to be negative 2 times what's inside to the negative 3, right? If this was x to the negative 2, it'd be negative 2x to the negative 3. But it wasn't just an x, it was a 4x minus 3, so I have to multiply by the derivative of 4x minus 3. And again, you might be comfortable enough just going, well, okay, that's just 4. So now it's a matter of simplifying. Let me just write it as 3 times 4x minus 2 to the negative 2 plus, let's see, it's actually minus, isn't it? Minus 4 times 2, 8. I've got a 3x plus 5. And I've got a 4x minus 3 to the negative 3. Now we need to simplify this. We don't leave negative exponents. And we could, write this way. I'm actually not going to do it this way, but just kind of set you up in case you want to do it this way. If you want to do it that way, you can, but then I expect you to find the common denominator and combine them into a single fraction. All right? But what I want to show you is the algebra of factoring, when we're factoring negative exponents and rational exponents. If you prefer to do the problems this way, where you express a quotient as a product and then use the chain rule, the only reason you're really going to want to do them this way, typically, is if you like simplifying the way I'm about to simplify. So remember all those factoring problems in the algebra review. I see that I have 2 factors. I'm just going to factor this. And we factor by factoring out the smaller power of, this is a 4x minus 3. So I have a common factor of 4x minus 3. I take the smaller of the two, which is negative 3. Here I'm left with a 3. I'm left with 4x minus 3 to the first power, right? I had negative 2. Negative 2 minus a minus 3. Negative 2 plus 3 is 1, so there's a power 1 there. And then minus 8 times 3x plus 5. And we factored this out, so it's gone. So that's 4x minus 3 to the negative 3. And then cleaning this up inside, let's see, what do we have? 12x minus 24x minus 12x. And minus 9 and minus 40. Hopefully I'm not making a mistake here. And so it's easy now to write this with no negative exponents because that's a factor now. So I get negative 12x minus 49, and then that factor just comes down as 4x minus 3 cubed. So play around with it. See what you like more. Maybe you would rather do the quotient rule. What do I do? You know, sometimes I do it one way, sometimes I do it another. I don't know what determines it. Sometimes it just looks like, oh, this would be a nice quotient rule, or especially if there's square roots or cube roots or anything like that. If there's a fractional exponent, typically I would do it this way for sure, because then we get to here, we just are factoring fractional exponents. All right, go give that next set of problems a try.